Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh, ah! Gosh, it's so difficult sometimes to get the piranha back inside.
All right, welcome to our first lesson in Calculus 3, really. So a lot of Calculus 3 is built on the idea of using things as vectors, so that's where we're going to start. And vectors, they have that fancy word vector, and everybody thinks, oh my goodness, is this going to be crazy? It's not going to be crazy. Vectors are very easy to deal with, and you will have no trouble whatsoever. So our basic introduction to vectors is the vector in the plane is basically a two-dimensional arrow or a directed line segment, that's another word we use, connecting 2 points. The 2 points that we usually connect are called the initial point and the terminal point. All right, so we have the initial point and then we have the terminal point. So if I come down here and I say, let's draw an arrow that starts at A and ends at B. A would be the initial point. B would be the terminal point. And if I draw a vector that connects these, that is the vector AB, right there. All right. So AB can be written in component form, where it's instead of parentheses, we have these pointy parenthesis bracket things. We can write them in component form as v sub 1 comma v sub 2, where v sub 1 is the horizontal component, in other words, how far you move left or right. Positive means you're moving right, negative moving left. And v2 represents your vertical component. Positive means you're moving up, negative means you're moving down. So if we want to write a b in component form, I'm going to write it like that. And to get from A to B, I go over, let's count it here, 1, 2, 3, 4, 5 to the right, and 1, 2, 3 up. So 5 right, 3 up gives me the vector 5, 3. If I want to write BA in component form, BA in component form is really going to go in the other direction. So if I draw it moving backwards, I now went 5 left and 3 down. So that's going to be 5, 3. But since I went left and down, I negate them both. So the coordinates of A are 2, 3, and the coordinates of B were 7, 6. What if I didn't have the picture and I couldn't count it? What could I do with the coordinates to get the component form of a vector? Well, 2, 7, 3, 6, wait, the difference of 2 and 7 is 5. The difference of 3 and 6 is 3. When you want to get a vector, let's call it vector V, your vector is x2 minus x1, y2 minus y1. That's how you get the component form of a vector. Now, one of the other things we really like to talk about is not only what direction are they going in, but how big is this vector? It's an arrow, but how big is it really? So how big is a vector is really a measure of what it's called its magnitude. The magnitude of a vector is the distance between the initial and the terminal point. Its notation is double bar, AB with an arrow, another double bar. Sometimes you'll see this written as a single bar. It means the same thing. And then a lot of people ask, well, wait a minute, doesn't the single bar mean absolute value? It absolutely does, pun intended there. It absolutely does, because absolute value has actually always been a vector, you just didn't know it. Absolute value, if I say 2, 3, 4, 5, 1, 0. The absolute value of 3 means how long is the segment that connects 0 on the number line to 3 on the number line. It's always meant a distance. So when you do the absolute value of -4, you have -4, 1 at 0. And how long is this segment? Still 4. So absolute value has actually always meant magnitude. You just might not have known that. So there you go. All right. Well, anyways, back to this magnitude thing. When we take the magnitude of a vector, you can do one of two things. Number one, you can use the distance formula with the coordinates. So the distance between 2 points when you make your vector is the change in x squared plus the change in y squared. So if I look at a and b here, when I do x2 minus x1 squared, I have 7 minus 2 squared. And then I have 6 minus 3 squared. And that's going to give me the square root of 25 plus 9, which is the square root of 34. I can also use the component form of the vector. So if I look at the vector AB, which is 5, 3, when I take the magnitude of AB is just the square root of the sum of the squares of the components. You take component 1 and square it. You take component 2 and square it. You get that, which is amazingly the same thing. All right, so I want you to take a second. I want you to pause this video. I want you to look at these coordinates, write PQ and QP in component form. Then I give you another one, QR, and I say, you know what? Find the components of R. And then last but not least, I want you to find the magnitudes of PQ and QR. So do that, and we will come back together in a moment. So press pause. All right, hopefully you pressed pause. Maybe you did, maybe you didn't, but hopefully you pressed pause here. And if you did press pause, when we come back, PQ in component form is going to be, well, how far is it to get from P to Q? Well, I'm going to kind of count in my head here and say PQ goes from an x equals -3 to an x equals 9. -3 to 9 means I went right 12, and 5 to -6 means I went down 11. So there's PQ. QP means I go in the other direction, so from 9 to -3 I went down 12, and from -6 to 5 I went up 11. And really what you should notice right now is that PQ and QP are almost identical, but they are negated. If you switch the order of the vector, you just negate the components. All right, and then last but not least on this page, find the, let's see, find, what do we have? QR is 2, 5, find the coordinates of R. Well, okay, so if Q is 9, -6, and QR is 2, 5, that means to get from Q to R, you go right 2, up 5. So that means R is right 2, up 5 from where Q was. And then last but not least, magnitude of PQ is going to be 12 squared plus 11 squared. Magnitude of QR is going to be, where was it, 2 squared plus 5 squared. So I have the square root of 144 plus 121, which is the square root of 265, and the square root of 4 and 25, which is the square root of 29. So hopefully that all makes decent enough sense. That's vectors, that's how they work. Now, there are some special vectors. There's a lot of special vectors, but there's some special ones. A couple special vectors, one of which is the 0 vector. The 0 vector is a vector with no direction and no length. It's 0, 0. You'll see it notated by a bold 0 or a 0 with an arrow over it. A unit vector is a vector with a magnitude of 1. Now, there's lots of unit vectors, so one example of a unit vector might be an easy one, 0, 1. That would be a unit vector. Another unit vector would be like the vector 3/5, 4/5, because if I take that and I look at the magnitude, I have the square root of 3/5 squared plus 4/5 squared, which is going to get me the square root of 9/25 plus 16/25, which is 1. That's a unit vector. Now, there are standard unit vectors. There's one called the I vector, which is the vector 1, 0. and another one called the j vector, which is 0, 1. And the reason these are important is because you can write vectors in component form and in what's called standard unit vector form, and that's when you use I and j to write the vectors. So if you want to write the vectors in component form and standard unit vector form, 3, negative 4 becomes the sum of multiples of I and j, so it's 3i minus 4j. So an example would be if I have these 2 points here and I want to write jk in component form and what sometimes I shorthand to ij form rather than saying standard unit vector form. I'll just say ij form. But anyways, if I wanted to write this vector in component form and ij form, component form for jk is negative 7, negative 2 to 7, I went down 5, negative 7, negative 5. In ij form, that's a negative 7i minus 5j. Okay, wait, why did I dot my I and my j with that? It's something we do so we don't have to write the arrows, because technically I and j are only vectors if they're bolded within text. And since we can't bold everything when we're writing it, or at least not easily, what we do is we put a little hat on the I and the j, and that shows that that's the vector I and the vector j. Sometimes you might also see this as negative 7i with an arrow over the top of it, maybe dotted, maybe not. 5j with maybe a dot and an arrow over it. That works too, but I usually use the little hats. Well, when we write things in standard unit vector form, what we're really doing is we're doing an operation on a vector. We're multiplying I and j by a number, and then we're adding those multiples together. So when you want to add or subtract vectors, it's super simple. All you do is add or subtract the horizontal and vertical components. So let's say 3 points have coordinates of ABC as shown. Find the sum of vector AB plus vector AC in component form. Well, first I should probably write vector AB and vector BC down. So vector AB is 1, let's see, negative 7. And vector AC is, let's see, I'm going to go up 6 and I'm going to go down 8. So AB plus AC is just the sum of those components. 1 plus 6 is 7. Negative 7 plus negative 8 is negative 15. That's it. And if you want to subtract, same thing. You just subtract the components. So AB minus AC is going to be 1 minus 6 is negative 5. Negative 7 minus negative 8 is 1. And there's the difference. Multiplying and dividing vectors. You can't. Don't try. You just can't do it. You're not allowed to multiply and divide vectors by vectors. It just doesn't happen. However, you can multiply or divide a vector by a scalar. In other words, a constant. This you can do. You just multiply and divide both components by the actual scalar. So if I want to use those points from before, and I want to find 4 times vector AB, that means I'm doing 4 times 1, negative 7, and what happens is the 4 just distributes to both of these numbers. So I get 4, negative 28. Now what happens to the length? If you multiply a vector by that, what's going to happen to the length of that? Well, if you multiply a vector by some scalar k, that just multiplies its length by k. So we're going to show that right now. So I want to show that the magnitude of 4ab, I want to show that the magnitude of 4, negative 28 is equal to 4 times the magnitude of regular vector AB, which was 1, negative 7. So over here, I would have the square root of 4 squared plus 28 squared. And over here, I would have 4 times the square root of 1 squared plus 7 squared. Ignore the negative, it's going to disappear anyway. So here I have the square root of 16 plus 784. And over here I have 4 times the square root of 50. And 16 plus 784 is the square root of 800. And over here I have 4 root 50. And if I take this guy and I divide by 50, you know what I'm going to get? I'm going to get 16. So the square root of 800 is the square root of 16 times the square root of 50, which is the same as 4 root 50. Now, obviously, I didn't simplify that all the way down, and I'll do that in a second, but you can easily see now that these match. And really, I could pull out another 5 from here, because 50 is 25 times 2. So this would be 25 root 2. I'm sorry, not 25, 20 root 2. And so would that. All right. So there is all of our vector stuff and operations on vectors, and there's a couple more things we can do with vectors. Remember we talked about those unit vectors, I don't know, 5 minutes ago? Something else you can do is you can create a unit vector. Well, why would I want to create a unit vector? Well, sometimes if I take a vector and it's this long, but I want another vector that goes in the same direction but that's only 1 unit long, I want this vector instead. So what we can do is we can make a vector that points in a certain direction but has the length that we want it to have. And that ends up being useful in a bunch of different scenarios. But in order to create a unit vector in the same direction as another vector, you just divide the vector by its own magnitude. This is called normalizing a vector. So let's say I want to find a vector in the same direction as AC that's 1 unit long. So I'm sorry, you got to flip back to the other page here. Let's take AC, 6, negative 8. So AC is 6, negative 8. If I want to find a unit vector, first I need to find the magnitude of AC, which is going to be the square root of 6 squared plus 8 squared, which is 10. And then the unit vector, which sometimes, but not all the time, we'll just call U for unit. The unit vector is really just going to be AC divided by its magnitude. So the unit vector is going to be 0.6, negative 0.8. And that is going to be 1 unit long and in the same direction. Okay? If I want to create a vector of any length in a certain direction, what you're going to do is you're going to create a unit vector first to get it down to 1 unit, and then multiply by the magnitude that you want it to have. So basically you shrink it down to the size that you want, kind of like what I did up here. You shrink it down to the size that you want, and then you take that guy and you stretch it a little bit to make it bigger. Okay? So let's say I want to find a vector in the same direction as BC that's 5 units long. So let's go back here. Where was BC? Again, I'm sorry, I had to change the page. So BC is going to be 5, negative 1. So if I want to take BC, which is 5, negative 1, and I want to create a vector that's 5 units long, first thing I need to do is find the magnitude of BC, which is going to be the square root of 26. And then I just take BC, divide it by its own magnitude, and then multiply it by 5. So one thing that you'll see a lot is we'll just make this like a coefficient out in front and leave it be, because that's pretty efficient, especially when we want to go and do other things with this vector. I don't want to have to deal with that coefficient all the time, and so we can leave it out front a lot. You could also change that to 25 over root 26 and negative 5 over root 26 if you want, but you don't have to. All right. And end of this page, almost there. Let's create a vector of a given length using angles. So if I want to find the component form of a vector whose initial point is the origin and has a magnitude of 8 that makes a 30-degree angle with the positive x-axis, magnitude of 8, 30-degree angle right here, and I want to know those components, you really just do some trig. My y component would be here, my x component would be there. I just do a little bit of SOHCAHTOA. And I say, well, y is y over 8 equals sine 30, right? So y equals 8 sine 30. I multiply the magnitude, in this case my hypotenuse, by the cosine and the sine of the given angle to get the horizontal and vertical components respectively. Y over 8 is sine 30, x over 8 is cosine 30, isn't it? Yes, it is. So my vector is going to be 8 cos 30, 8 sine 30. And the cosine of 30 is root 3 over 2. So this is going to be 4 root 3. And the sine of 30 is a half. So that's going to be 4. And yeah, there you go. So there is our introduction to vectors. We're going to do a lot more with them. So I hope you enjoyed that. We are always going to end with a joke here because I love ending with stupid jokes. So this one is going to be, why did the zombie get an A on his test? Because it was a no-brainer. Rah, rah, rah. I know, it's not that funny. You're not really laughing, but I'm going to tell bad jokes anyway. All right, enjoy the rest of your day, evening, morning, whatever it happens to be while you're watching this. And we will reconvene doing more calculus sometime soon.